Hey, hello everyone. My name is Christian Theobalt. I'm a professor at the Max-Planck-Institute for Informatics, and I'm giving this presentation together with Michael Zollhoefer, who is a postdoc who's working with me in our research group, Graphics, Vision, and Video. So what we are interested in is research problems that live on the boundary between computer graphics and computer vision. In particular, we are interested in methods to build models of the real world in motion. So I'm going to start with this a little bit, what types of problems we are interested in, and then in the second half of the talk, we are also going to speak about one of our recent projects on face reconstruction in a slight bit more detail, including also a live demo of face reenactment, so stay tuned. So when I say building models of the real world in motion, what does that actually mean? I think the easiest if I start with an example of our research. So this is a problem which we call markerless performance capture. The idea here is that we would like to reconstruct by placing a person in a studio equipped with 12 video cameras in this case, highly detailed models of the deforming surface geometry of the person, including also of the deforming geometry of the clothing. And we want to do that just from video without markers in the scene. Now, this is a project which has kind of been our research state of the art like 5 or 6 years ago. Most of the rest of the talk is going to be about newer stuff. Now, we are doing basic research, foundational research. We are not developing specific applications, right? We are basically developing the algorithmic ingredients of how reconstruction technology may work, let's say, in 10, 15 years from now. But nonetheless, also for us, it's inspirational to think, where could actually such technology be used in the end, right? And I want to show you a few examples for where I think this would be very useful. So on one hand, this dynamic reconstruction technology can be an enabler in content creation, for instance, in visual effects like virtual avatars, virtual actors for movies or games or virtual reality. Also for telepresence, like 3D telepresence, where you want to create like a 3D image of a moving person that is teleported somewhere else. Of course, dynamic scene reconstruction is also an important ingredient in virtual reality, but in particular in augmented reality. Because what you want to do there is you want to augment a real moving scene with virtual computer graphics content. In order to do that, you need to first reconstruct the scene. You need a model of the scene. You need a model of the motion in order to be able to augment it. Like this is a little mock-up video actually. That's a vision how it could at some point work. But a lot of the basic problems that are needed for that are still not entirely solved. Then also these technologies are important, for instance, in like autonomous systems where like cars that have a bunch of sensors that need to perceive their environment, what is the motion around, but also autonomous robots that need, for instance, interact with things in the world, need to grab certain objects and see how they deform. And then finally, it is also an ingredient of maybe the next generation of human-computer interaction techniques, where you need to interpret the way how humans move, how they gesture, how they interact with robots. So this is a compendium of fields where this dynamic scene reconstruction technology could be of use. Now, the problem here is that in order for many of these things to become reality, these dynamic scene reconstruction techniques actually need to work in unconstrained, general, real-world scenes. Not in a studio, like I showed to you, right? So in a sense, they need to work in scenes like this, right? So this is how a real-world scene looks like. Maybe not in terms of activity, maybe that's not representative here, but certainly in terms of complexity. There's a lot of things in the scene, a lot of objects that deform arbitrarily, that occlude each other, there is uncontrolled lighting and so on. And we are still far away from just putting a few cameras there and getting very detailed models of everything in such a scene. So ideally, that's where we want to go in a couple of years from now. Like just put a bunch of cameras, or in the end, maybe just one, and get detailed models of everything there. So we are not quite there yet, right? But we've taken a few important steps in this direction, and I want to show you a few of them. So one of the steps we took is in the area of markerless motion capture. So for you to understand what that means, I first have to explain to you what marker-based motion capture actually is. So marker-based motion capture is the classic way of doing motion capture, which you see here. So basically you put a person in a special suit with markers on, you have a bunch of special cameras that record these markers, and from that you get a 3D motion of the skeleton. Now, this is something used in content creation, in sports, and biomechanics. But the problem is, of course, this is quite complicated. I mean, you have to change the scene with a suit. So ideally, you want to do this from video alone. And this is what we have been working on. So what you see here is one of our latest results. It's a method to do real-time 3D motion capture from video recorded in general scenes. So we record this scene here with 8 video cameras and can then also here in the sports studio setting capture the 3D motion of this boxer here at very high detail in real time. Now the method here can also be applied in other scenarios. So we've, for instance, also done motion capture in a scenario where I don't think you've ever seen this before, which is here underwater. So we placed a bunch of cameras here in the water and actually do motion capture from that footage. So, and since we don't need to have any special markers in the scene, we can use that in very general environments. Now, this is something that we've been working on for many years, and it has started to mature, and actually, some folks from my group decided to spin off a company. It's called The Captury, and they're actually selling a system which can do that in real time for several people in a general scene, or which can also do it with footage that you recorded, for instance, with GoPro cameras, which is what we actually used here. So we used GoPros to capture these motions. So far, I've mostly talked about full body motion, but what we're also interested in is hand tracking. So hand motion capture is almost a research problem in itself in the computer vision community because of its relevance for interaction and communication. So what you see here is one of the first methods that we developed for real-time 3D hand tracking with a single camera. So the camera you see is the one on the top left. It's actually a depth camera, so it's not a normal RGB camera. It measures the depth of every point in the scene, but it's still a consumer product. It costs like 100 euros, and you can buy it. And as you can see here, we get the full articulated motion from that sensor. And what's interesting is it also works when you put the camera in an egocentric perspective, which is very interesting for augmented reality. So you put the camera to your head-mounted display. Now, of course, what is usually the case, right? If you're moving your hand, most of the time you're not moving your hand in free space. You're usually interacting with things. And that is currently one of the open research questions which we are looking into. For a computer, it's extremely hard to actually track the hand motion when the hand is interacting with an object because there are much more occlusions created. And what you see here is actually the first time we show it out of our lab, so our latest project which we show in 3 months at the European Conference on Computer Vision, one of the first methods to track both the articulated hand as well as the object in 3D in real time with a single camera. Thanks. So far I've mostly talked about skeleton tracking with single cameras. I started my presentation with surface reconstruction. We are still interested in surface reconstruction methods, and I want to show you one of our results here. So what you see here is essentially performance capture, so detailed shape reconstruction of moving humans, but now not with 12 cameras in front of a green screen, but only with that freely move. So, and one of the important ingredients here, and that's also something that's going to be used in the second part of the talk, is what we are doing here is we are not reconstructing only the deforming geometry. We are also estimating the reflectivity of the surfaces in the scene, as well as the lighting in the scene, which we call inverse rendering. And that turns out to be an important algorithmic ingredient in order to go to a lower number of cameras and in order to go to a more general set of scenes. So one specific type of deformable scene which we are interested in are faces. So we have done a lot of work on dynamic face reconstruction. And now I hand over to Michael, who is going to talk a little bit about a project we've been working on recently, which is called face-to-face, real-time face reenactment. And I hand over to Michael.
So hi, everybody. I want to tell you a bit about our face-to-face project. Face-to-face is short for real-time face capture and reenactment. So maybe as a starter, what is it all about? We take a standard webcam, we film a source subject, and we transfer his motion, his facial motion, in real time to a target YouTube video. Here it's George W. Bush. So how does this look? Looks like this. And as you can see, the full facial motions are transferred. This includes the mouth, the eyebrows, and the cheeks. Okay, so now that you know what we are talking about, thanks a lot. Let's have a short overview of how this works. So first I will explain you about how to synthesize real-looking images of faces. Then we will look at monocular face reconstruction, so reconstruction of faces from a single view. And finally, I tell you about the reenactment. Okay, first part. So faces are all around us, but if you think about what does influence the appearance of a face in an image, it's for sure the pose of the face. So basically, where in space is it? How is it rotated? But it's also the facial shape. How big is the nose? How big is the head? But also like other properties like skin reflectance. Like if you have a darker skin, your face looks darker and so on. Faces are not static, so there's a lot of change due to expressions. And also illumination has a big difference. So if the spotlights would be turned off, you cannot see me anymore. The middle part, shape, albedo, and expression, we call a multilinear face model. And actually, I will show you a live demo of how this looks in 3D. Takes a bit to start. Okay, so this is our face model. It's full 3D. It goes up to the ears. And this is the average face, which has been computed out of 200 subjects. And this slide, oh. So can we fix that somehow? I mean, let's try the presentation again, if you can see this. Okay. Let's see. Nope, doesn't work. Okay, let me just continue with the talk. I show you the demo later. Afterwards, I hope it's fixed until then. Not sure what's going wrong there. Okay, so basically, if you look at the demo, we have these sliders here, and by moving the sliders, you can control facial shape, facial albedo, and also expressions. I show you that later. And if you can produce really realistic-looking faces with that. In the next step, when we want to reconstruct actually the facial geometry, given an input image, what we actually want to do is we want to find these slider positions such that the synthesized face matches the input image, so they look alike. And now you can think of what you could do. You could frickle around at these sliders, but this is tedious and time-consuming. So what we as computer scientists do, we develop algorithms which automatically find suitable slider positions such that the synthetically produced image looks like in an input image. And we do this by an approach which is called analysis by synthesis. So basically, we take an input image, we overlay our model, we compare our model based on color to the input image, and we get the difference. Basically, what's the difference between the two? And then we try to minimize this difference somehow, because then we have a good fit. And we also add some regularization terms that we don't get weird facial shapes. And we plug everything into this energy function, and what we want is the minimum of it. If we find the slider positions which minimize this function, we have a good fit of our scene. And this is actually a super hard problem. It's a nonlinear problem. You need a lot of compute to do it. What we decided to do at some point, we use graphics cards, which you have in your gaming machines, I guess, to solve this problem. And graphics cards are super nice for that, because you can crunch a lot of numbers fast. You have a lot of data parallel compute power. And this allows us to do this in below 33 milliseconds. Below 33 is really important, because if you manage to do that, you can reconstruct faces at the capture rate of the camera, which is normally 30 hertz. So you can do it live, and I hope I can show you later if this issue is fixed. Good. How does this look? It looks like this. Input is a video. Here it's a speech of Obama. And output is a 3D mesh, which is moving, and he's doing the same. Okay, so now we know how we get from a single image, a 3D model. Now let's have a look at reenactment. Here it's a bit different. We have two input videos. We have a source video and a target video. And we reconstruct both of them using the approach I presented. So we get the 3D geometry. And now we can copy the facial expressions from source to target. You see that on the right. And afterwards overlay it back on top of the target video. So I'm doing now what my coworker was doing. And if you add in texture now, should happen shortly. It looks photoreal, and my face is moving, even though in the input video I was not doing anything. Okay, hopefully we try this again with a live demo.
Okay. So let's see if we can get the live demo here to work now. Can you switch the mic on?
Can you switch the mic on, the other one? And could you just switch to my screen? So we had it at the start.
All right, so we are trying now to start the demo app here to show you actually a live demo of this application. It takes a bit of time. That looks good. So now it starts basically by loading the model, loading the videos, doing some pre-processing on the target video, computing the lighting there, computing expressions there. And then what's going to happen actually is Michael's face is going to be tracked from the webcam that is on top of the machine. So once this is running up, still takes a bit to load. So that's all proof, you know, it's not a video. This is really a live demo running on this laptop. So, I mean, it needs a bit of compute, so it's not maybe exactly the standard laptop. So this is a gaming machine. It has a high-end GPU in there in order to get the full frame rate. Just a few more seconds. All right, this is looking good. Okay, what you see here now is left is the input image, and on the right, you see the real-time face tracker running. So, and you see it's really stable. It also works quite well actually under changing lighting. And I can actually provoke that a little bit, right? So it's strong lighting change is still very stable. And the reason for that is that we are estimating the lighting and the albedo of the face in real time together with the shape, right? And what we can do now is basically we can, for instance, also add a texture. No, first we need to basically personalize this model a little bit more to Michael. So this is, if you're interested in, is running a bundling step in real time, or it takes a few seconds actually. So that personalizes the face identity as well as the albedo map of Michael's face. So now this is the better model, and what you see on the right now is actually the rendered face model overlaid with a video, right? And now we can also put a texture, for instance, on. Can you switch on like one of our logos? Because we reconstruct the albedo texture, we can also change it. Or maybe we can't. All right, so let's go then to the reenactment demo. So we can do this now in real time on the source phase. And now what we can do is we can, in real time, transfer his expression onto a target phase, which is in this case Arnold. And now when Michael changes his face expression, Arnold is mimicking what he's doing. All right, so and now if I do this, yeah, it still works pretty stably. Sometimes you may see a bit of glitches, but it's not too bad, right? All right. So I think that's the end of our presentation. We thank you very much for your attention. If you have questions, we're open for that.
Right. I think we have some time for questions. Does anybody have a question for the two gentlemen here? We'll bring a mic out to you. No? Okay.
There's one over there. There are questions over there.
Well, it is a short time frame for the questions, but yes, we'll take one or two.
So if this technology becomes so seamless that you can't distinguish that it's happening, don't you envision that there's going to be a lot of fraud, for example?
Yeah. Okay. I mean, this is a very good question, right? So the thing is, I mean, we are not. Maybe I should tell a bit about the story. We didn't develop this as the application of face reenactment. The reason why we showed that in reenactment is because it indirectly shows how well we reconstruct the lighting and the shading in the scene. And this was a nice effect which we discovered. However, at the same time, we are a public research institution, and it's either way our duty to actually show what the potential of technology is, but also to basically raise awareness of what actually can be done with modern image reconstruction methods. So it's, in a way, it's actually a purposeful provocation that we did, right? Now, if you would ever make this commercially available, you of course would like to make sure that there are no such possibilities given. You could use watermarking schemes just to make sure that it's always easily recognizable that something has been modified. Yeah.
Can the computation be moved to the cloud at some point?
Yes, I think so. I think what you could do now is essentially, I mean, maybe not with real-time feedback. I'm not entirely sure about this if you really want to stream it back. But you could certainly record a clip, put it send it to a server, do the computation there. You saw it runs in real time, takes a few seconds, comes back. Yeah.
Awesome. Thank you very much, you guys.
Thank you.
Give it up one more time for them.